Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate Programs Postgraduate Certificate, Certificate in Condition Monitoring, COMO, Med 00 to Mechatronics, Block-1 Sensors and Transducers, Unit-1 Introduction to Transducers and Sensors, 1.1 Introduction. Mechatronics can be defined as mechanics controlled by electronic systems. Sensors are the eyes and ears of the control system. They can be used to provide real-time information for directly controlling processes as well as provide information for data logging purposes, for example, to provide a count of the daily units produced off a particular manufacturing line. A sensor can be formally defined as device that maps a physical or chemical quantity to a signal, normally electrical. A transducer is defined as a device that converts a signal from one form of energy to another form. For example, a piezoelectric crystal, properly cut, can be called a sensor, whereas it becomes a transducer with appropriate electrodes and input-output mechanisms attached to it. Quite often the terms sensor and transducer are being used interchangeably. Sensors can be broadly classified in two categories: discrete event and continuous. Discrete event, or on-off sensor, changes its state based on the occurrence of some external event. These sensors typically only give knowledge of two states based on the condition being sensed. They are based on either mechanical, electrical, or optical technology. A continuous sensor provides information over the continuous range of operation of the process and are commonly used in continuous control applications where the process is being regulated based on continuously sensed attribute data. They are based on electrical, optical and acoustical technologies. Objectives: after studying this unit, you should be able to describe different types of sensors and transducers and understand the concepts of digital to analog conversion and vice versa. 1.2 Active and passive sensors. The sensors can be classified as active and passive. A passive sensor has no power supply and all the energy it delivers to the next stage, the signal conditioning, is drawn from the measurand. Passive sensors are also known as self-generating sensors. An active sensor is a modulator and can therefore deliver more energy to the next stage than it draws from the measurand. If the power supply is DC, the output is modulated by the measurand and has the same frequency. If the supply is AC, the output is the carrier frequency with sidebands at signal frequency. 1.3 Basic requirements of a sensor. Transducer. A transducer is normally designed to sense a specific measure and/or to respond only to that particular measurand. A complete knowledge of the electrical and mechanical characteristics of the transducer is of great importance while choosing a transducer for a particular application. Often, it is deemed essential to get details of these characteristics during the selection of instrumentation for the experiment concerned. The basic requirements are ruggedness, ability to withstand overloads, with safety stops for overload protection, linearity, ability to reproduce input-output characteristics symmetrically and linearly. Overall linearity is the main factor considered. Repeatability, ability to reproduce the output signal exactly when the same measure and is applied repeatedly under same environmental conditions. Convenient instrumentation. Sufficiently high analog output signal with high signal-to-noise ratio, digital output preferred in many cases, high stability and reliability, minimum error in measurement, unaffected by temperature, vibrations and environmental variations. Good dynamic response, output is faithful to input when taken as a function of time. This effect is analyzed as the frequency response. Excellent mechanical characteristics that can affect the performance in static, quasi-static, and dynamic states. The major effects are mechanical hysteresis, manifestation of imperfect response of the sensing elements, integrated over dimensions of the strain transducers. Effect depends on the raw material used, aging, etc. Viscous flow or creep. Effect due to viscous flow in the material of the sensing element. Magnitude increases with increasing load and temperature. Materials with low melting point show larger creep values. 2. Elastic after effect. A continued deformation when the load is applied and kept constant. This effect decreases with time. Like creep, there is a similar relaxation towards the original position when the load is removed. Virtually no deformation is observed. You will study more about these effects in Unit 2, built-in integrated device with noise, asymmetry, and other defects, minimized. 1.4 Discrete event sensors. A discrete event, or on-off, sensor changes its state based on the occurrence of some external event. They may be contact type, for example, a limit switches, or non-contact type, for example, proximity switches and photoelectric sensors. These are being described in detail in this section. 1.4.1 Mechanical limit switches. Mechanical limit switches typically consist of a mounted actuator arm that operates a set of electrical contacts when the arm is displaced. Two examples are shown in Figure 1.1. Figure 1.1a illustrates the operation of a lever-type limit switch, and Figure 1.1b illustrates a plunger or push-type limit switch. In the case of the lever type, the actuator arm is a rod, 1, connected to a lever shaft, 2, which is free to rotate when the rod is displaced. When the forces displacing the rod are removed, the lever shaft is returned to its normal position by a return spring, 3. The lever shaft has a roller mounted on its bottom, 4, which rotates a rocker, 5, as it changes position from right to left. This mechanical action operates one or more sets of contacts, which are mounted on the other side of the limit switch, as shown in the back view. The rocker shaft is connected through the housing to the contact lever assembly, 6, the head of which moves a set of electrical contacts, 7. The electrical contact may either be closed or open initially. The action of the actuator and lever arms takes it from its normal or deactivated state to the other state. Hence, a normally open limit switch will be closed when activated, and a normally closed limit switch will be opened when activated. Figure 1.1b illustrates the more direct action of a push-type limit switch. It shows a set of contacts operated from the contact lever assembly. Contact set AB is normally closed, set CD is normally open. When the lever is depressed, each contact goes to its opposite state. When installed, the user wires the appropriate contact pair back to the controller, which distinguishes the state of the system by reading the voltage or current, on-off, supplied through the contact. Limit switches come in several varieties and designs. Figure 1.1 simply shows two concepts. They are designed for heavy-duty applications in which there is physical contact between the actuator and the process being sensed. For example, limit switches are often used on machine tools to limit the travel of a machine axis. They are sometimes used in materials handling applications, e.g. to indicate the passage of a part along a conveyor. They are typically designed to handle relatively high voltages, both AC and DC. This means they cannot be directly wired to the input port of a computer without having their signal converted to TTL level. Look at the screen. 1.4.2 Proximity limit switches. The term proximity switch, sometimes called proximity sensor, refers to a non-contact sensor that works on the principle of inducing changes in an electromagnetic field. The proximity switches most commonly used in the manufacturing environment are the inductive proximity switch and the capacitive proximity switch. Inductive proximity sensors are designed to operate by generating an electromagnetic field and detecting the eddy current losses generated when ferrous or non-ferrous metal target objects enter the field. The sensor consists of a colon, a ferrite core, an oscillator, a trigger signal level detector, and an output circuit. As a metal object advances into the field, eddy current are introduced in the target. The result is a loss of energy and smaller amplitude of oscillation. The detector circuit then recognizes a specific change in amplitude and generates a signal, which will turn the output on or off. A metal target approaching an inductive proximity sensor absorbs energy generated by an oscillator. When the target is in close range, the energy drain stops the oscillator and changes the output state. The active phase of an inductive proximity switch is the surface where a high-frequency electromagnetic field emerges. A standard target is a mild steel, 1 mm, thick, square form with side lengths equal to the diameter of the circle of the sensing surface, or 3 times the normal switching distance, if this is greater than the diameter of the sensing surface circle. The distance at which this approaching target activates changes state of the proximity output is called normal sensing distance. The size, shape and material affects the sensing distance in the following fashion. Rounded targets may reduce the sensing distance. Non-ferrous materials usually reduce the sensing distance. Targets smaller than the sensing face typically reduce the sensing distance. Targets larger than the sensing face may increase the sensing distance. One of the shortcomings of the inductive proximity switch is that it can only sense metal objects. The capacitive proximity switch, on the other hand, can sense non-metallic objects as well. It uses a resistor capacitor, RC, oscillator to generate a directed magnetic field. Introducing an object within the magnetic field causes a change in capacitance, which is detected by the control circuitry, which in turn operates an electronic switch that outputs a signal to the controller. Proximity switches have relatively short ranges, typically from 1 to 60 mm, therefore, they must be used in situations where the target is allowed to come close to the sensor. 1.4.3 Photoelectric sensors. Photoelectric sensors are non-contact devices that output a signal in response to the interruption of a light beam. The components of a photoelectric sensing systems are shown in Figure 1.2. The two main components are the emitter and the receiver. The light source is a light-emitting diode, LED, and LED is a solid-state semiconductor that emits light when current flows through it. LEDs are manufactured to produce light in the visible range in the near-infrared range. The light source is paired with a receiver, which is light-sensitive transistor, called a phototransistor. A transistor conducts when its base is forward-biased. This is done by applying a small amount of current on the base LED. A phototransistor operates in the same fashion except that the base is biased by the energy from a light source incident on it. Phototransistors are manufactured to be sensitive to light within the spectrum of the emitter. Look at the screen, Figure 1.2, a photoelectric sensor. A photoelectric sensor system comes with an oscillator that modulates or pulses the LED on and off at very high frequencies. The receiver is tuned to the same frequency, which allows it to differentiate between light from the emitter and ambient light. 1.4.4 Fluid flow switch. A discrete event sensor commonly used in process is the fluid flow switch. This device is analogous to a limit switch in mechanical systems. It is usually employed as a device to detect when a fluid traveling in a pipe is over a specified volumetric flow rate. Such a sensor can be used to govern the speed of an upstream pump, reducing it when the flow is too fast. There are different implementations of a fluid switch. One implementation is shown in Figure 1.3. Here a float is placed in a trapped column that is in line with the fluid flow. A magnetic ring is seated on the float and, in the absence of pressure, the movable float is retained in the seated position. Water pressure raises the float proportional to the flow rate. A switch is positioned at a height where the float will be displaced when the triggering flow rate is reached. Typically, the switch is a reed switch, which consists of two leaf springs sealed in a glass. These leaf springs come together when subjected to a magnetic field. This closes the circuit, providing an input signal to the controller. Look at the screen figure 1.3, a flow switch, 1.5 continuous sensor. The term continuous sensor is used to describe a device that converts one measured physical quantity into another that is proportional to the measured physical quantity. The measured physical quantity might be position, velocity, or temperature. The converted physical quantity is typically one that can be used in an electronic circuit, such as electrical resistance. 1.5.1 Components of a continuous sensing system. The components of a sensing system and their relationship to a digital controller are shown in figure 1.4. Each component of the chain has a unique purpose, which shall be briefly explained. The sensor takes the actual physical input, such as force or temperature, and provides an output that can be used by an electronic measurement circuit. The measurement circuit is used for calibration and reading of the sensor output. The output of a measurement circuit will be a voltage or current that is proportional to the physical property of the system being measured by the sensor. For example, it may be a voltage whose magnitude is proportional to a force being measured at the sensor process interface. Sometimes a signal will have electronic noise or be too weak to process directly from the measurement circuit. In such cases, the signal may be filtered to remove the noise or may be amplified for further processing. This is the role of signal conditioning. Since computers and controller processors are digital devices, any analog signal will have to be digitized before it can be read by the computer. An AD converter provides the conversion. In cases where the sensor signal is already in digital form, such as that emitted from an optical encoder, such step is unnecessary. Finally, the signal is presented to the computer for processing. 1.5.2 Analog to digital conversion. When a sensor provides an analog voltage input to the controller, it will be necessary to convert the signal to digital form for computer processing. This is the role of the AD converter. This is accomplished by sampling the analog input at discrete intervals of time and mapping each sample into one of the discrete quantizing levels of the converter. An AD converter has two discrete quantizing levels, where n is the number of bits in the register of the AD converter. Figure 1.5 illustrates a 2-bit AD converter with a full range voltage of 6.0 volts, i.e. it is designed to be used over the range 0 to 6.0 volts. The mapping of voltage into a binary count is shown in Table 1.1. An AD converter maps a voltage range to a binary count. In general, the analog signal will fall into one of the quantizing levels of the converter. There are 4 quantizing levels and 3 incremental changes of 2.0 volts each. Table 1.1. Analog input and binary output. Look at the screen. The resolution of an AD converter is determined by the step size, which is 2.0 volts. The percent resolution can be completed using the following equations. Percent resolution is equal to step size upon full range into 100%. 1% resolution is equal to 1 upon 2 minus into 100%. In the above example, therefore, the percent resolution is. The term accuracy is used to describe the worst-case error between the actual analog input signal and the recorded value as determined from the digital reading. In general, the accuracy is 1/2 of the resolution. 1.5.3 Digital to analog conversion. The basic process of taking a binary number and converting it to a voltage level is illustrated for a 4-bit binary DA converter in Figure 1.6a. With 4 bits provided by the computer. 2. 4 is equal to 16 possible input states can be presented to the DA converter. The desired range of the output voltage must be designed into the DA device. For figure 1.6, the full range of the device is 0 to 15 volts. The input binary count can range between 0 to 15. Since there are 15 increments over the full range of the 15 volts, each increment of the binary count equals volts. Table 1.2 illustrates the relationship between the binary input and analog output. Each increment of the binary count adds 1.0 volts to the output voltage. Figure 1.6, digital to analog converter. A. 4-bit DA block diagram. B. Implementation of a 4-bit DA converter. Table 1.2, binary input and analog output. There is a relationship between the binary position weights and the output voltages. In particular, A1 in each successive binary position results in a doubling of the output voltage. This is a clue to the way in which DA converters are constructed, which is illustrated in figure 1.6. B. Each binary output signal from the computer at 5 volts controls an electronic switch. Each electronic switch is used to connect or disconnect a branch to a reference voltage, Vref. Current will flow in connection branches. The op-amp is a device that produces a weighted sum of the input voltages. The op-amp voltage, Vout, is the output voltage of a ladder of resistors which are electronically switched, connected to a reference voltage, Vref. Hence, by placing the appropriate binary code on B0, B3, the voltage level Vout can be produced. The values of the resistors on the ladder are incremental in binary powers, I2R, 4R, 2NR. Hence, from the law of passive linear circuits, the current in each branch of the ladder is, look at the screen, where IA is the current in the junction point A, Vref is the reference voltage, R is the resistance basis, AI is a binary indicator, 0 or 1, of whether the ith bit position is off or on, where the first position is the most significant bit, MSB, and N is the number of bits in the output resistor and, therefore, the number of branches in the ladder. The above equations can be combined to yield the following function for ADA converter. 1.6 Transducers. A useful way to classify transducers is on the basis of the physical property the device is intended to measure. The important properties discussed in this section are position, velocity, force or pressure, temperature. 1.6.1 Position transducers. Position transducers are widely used in servomotors, linear position tables, and other applications where precise position is important. In this section we will discuss 4 analog position transducers, potentiometers, linear variable, differential transformers, floats and resolvers, and 2 digital position transducers, the optical encoder and ultrasonic range sensor. A. Potentiometers. An often used position sensor is a potentiometer. The potentiometer is composed of a resistor and a contact slider that allows position to be made proportional to resistance. There are linear and rotary potentiometers, depending on whether the displacement to be measured is linear or angular. An angular potentiometer is shown in figure 1.7. Potentiometers are quite inexpensive, very rugged, and easy to use. However, they are not as accurate as some other position transducers. B. Linear variable differential transformers. The linear variable differential transformer, LVDT, is a high-resolution contact transducers. As figure 1.8 illustrates, it is constructed with 3 coils, 1 primary and 2 secondary. A magnetic core sits within the coils. Figure 1.8. Principle of a linear variable differential transformer. A. Operation of LVDT. B. Core displacement and voltage out. If an alternating current is imposed in the primary coil, a voltage will be induced across the secondary coil. The magnitude of that voltage is a linear function of the position of the magnetic core. Deviations from the null position of the core are translated into voltages by the equation is equal to 1.7, where Vo is the change in output voltage, K is a proportionality constant and X is change in position. LVDTs come in varying size. A typical limit to travel is in the range of 750 mm. The resolution of an LVDT is excellent, easily able to measure displacement below 0.25 mm. Since this is an analog device, the limits of resolution are usually governed by the resolution of the AD converter. It is readily apparent that the LVDT has an advantage over the potentiometer as a position measurement device. Since its core does not touch the coil, there is no mechanical wear that would result in deterioration of performance over time. On the other hand, it is a more expensive transducer, justifiable primarily where very high and repeatable accuracy is required. See, resolvers. The resolver, shown in figure 1.9, is a rotary transformer. The primary winding is on the rotor and the secondary windings on the stator. The secondary windings are set 90 degrees apart. An alternating current is imposed on the primary winding. As the shaft is rotated by the device where position is being monitored, the voltages on the secondary windings will vary as the sine and cosine of the angle of the rotor. The two output voltages can be converted to a binary count using a resolver to digital converter, RDC. This device combines the circuitry necessary to interpolate the output voltages into angular positions and the AD circuitry required to digitize the result. The resolver is a non-contact transducer. Unlike the rotary potentiometer, it will not lose accuracy due to wear. The high precision of the resolver is usually limited by the AD converter, which converts the analog voltage into a digital count. Typical AD converter incorporated RDCs have 12 to 16-bit resolution. D. Optical encoders. An optical encoder is a digital position measuring device. It is available in both linear and rotor construction. Figure 1.10 shows the principle of an optical encoder in rotary form. A slotted disc is rotated in the path of a photoemitter detector pair. The emitter is typically a light-emitting diode, and the detector is a photosensitive transistor. When light is incident on the base of the transistor, current flows from collector to emitter. As the disc rotates, the light will be alternatively blocked and allowed to pass. In the blocked state, the transistor will stop conducting. The voltage output from the detector circuit is a sawtooth. This is fed into a Schmitter trigger, which is a digital device that converts the sawtooth pattern into a square wave. The square wave, with amplitude of 5 volts, is digital data in a form that is readable by a digital controller. It is typical for the detector circuit to output a high signal when light is blocked and low signal when a slot is encountered. Float transducers. Float transducers are the simplest method of measuring continuous position, height or level of a liquid in a tank. Floats are widely used in process industries in which batches of liquids are feeding production processes. There are different implementations of a float. One simple device is shown in figure 1.11. Here a float is attached to a rod that moves the wiper of a rotary potentiometer. Figure 1.11. Principle of a float transducer. F. Ultrasonic range sensors. For continuous measurement of a level in a tank, floats are being supplanted by ultrasonic range sensors, an example of which is shown in figure 1.12. Ultrasonic sensors use pulses of sound to measure distance. A transmitter senses out a pulse, I reflected against the fluid of which the level is being measured. When the transmitter sends out the pulse, it simultaneously initiates a timer circuit that counts clock cycles. A receiver, housed with a transmitter, receives the reflection of sound. The received signal terminates the timer and initiates a computation of distance. A microprocessor computes distance based on the speed of sound through the medium, typically air. The microprocessor may take several samples and compute an average to obtain a more accurate measurement. The reflected signal will travel to D during the period that the timer is on, T. If V is the velocity of sound in the medium, the distance between transducer and liquid level is equal to delta 1.8, 1.6.2 velocity transducers. Velocity transducers are used for speed control. We shall describe the primary, digital, optical encoder, and analog, DC tachometer, velocity transducers. A. Optical encoders. Since velocity is the positional change with respect to time, any positional transducer can be used to measure velocity. If θ1 and θ2 are two sequential, angular positions of the encoder given in radians, then is equal to 1 upon 1.9, whereas the instantaneous angular velocity in radians sec and t is the increment of time between sequential position changes. B. Tachometers. The basic analog velocity measurement device is the tachometer, or generator. This device can be based on the operating principle of an AC generator or a DC generator. The principle of a DC machine will be covered in detail in the next unit. As shown in Figure 1. 13. A DC tachometer consists of an armature, rotating conductor, mounted on the shaft of a device whose angular velocity is to be measured. The stator, or stationary component of the tachometer, is a permanent magnet. As the rotating conductor passes through the magnetic field, a current is induced in the conductor, resulting in a measurable voltage at Vout. In an ideal tachometer, the relationship between speed and velocity is linear. Simply put, upon is equal to 1.10, where k is the tachometer constant. Since the tachometer is an analog device, AD conversion is required. 1.6.3 or pressure transducers, force sensors are used extensively in automatic weighing operation in the process industries and in robotic applications when it is necessary to control gripping pressure. In this section we shall examine two analog transducers, the load cell and the strain gauge. A. Load cells. A load cell is used in processes where precise weighing is required. It can be implemented using a strain gauge or a LVDT. Figure 1.14 illustrates a load cell implemented by using a LVDT and a spring with linear force displacement. The appropriate transfer function is equal to delta 1.5, where F is force, K is the spring constant and D is the displacement from the unloaded rest position. Figure 1.14. LVDT used in weight measurement. B. Strain gauges. The most widely used pressure and force-sensitive transducer is the strain gauge. The principle of the strain gauge is based on the resistance properties of electrical conductors. Electrical conductors possess resistance based on the relationship delta is equal to by upon A 1.12, where R is resistance in ohms, ρ is resistivity constant, which is a property of the specific conductor material being in the wire. It is measured in the unit of ohm cm, L is the length of the wire in cm2, and A is the cross-sectional area in cm2. Since the resistivity is a constant, a change in the length and or area of the wire will cause a change in the resistance. This phenomenon is called piezoelectricity. 1.6.4 Temperature transducers. Temperature transducers are used extensively in process industries such as chemical, food and pharmaceuticals, where control of temperature during manufacturing is important. Three commonly used temperature transducers are the thermocouple, the resistance temperature detector, RTD, and the thermistor, A, thermocouples. When a temperature differential exists across the length of a metal, a small voltage differential will exist due to the migration of electrons in the metal. By joining two dissimilar metal wires together at one end, a small current will be induced at the junction due to differences in the molecular structure of the metals. This is shown in figure 1.15. Point B. The other ends of the metal wires is held at a reference temperature. For dissimilar metals at a given temperature, the density of free electrons are different. This results in an electron migration at junction A, causing a small current to flow from one metal to other. This small induced electric differential with proper signal conditioning is measured at point C. The electric signal has the property of being linear with the temperature differential between points A and B. In particular, a simplified model is of the form V out is equal to alpha into T minus T ref, where V out is the induced voltage, alpha is a constant in volts degrees K, and T ref are the measured temperature and the reference temperature respectively. B. Resistance temperature detectors, RTD. The RTD temperature sensor is based on a particular property of metals wherein the electrical resistance changes with temperature. In particular, as temperature increases, so does electrical resistance. This is due to the fact that a higher temperature in a metal results in electron vibrations that impede the flow of free electrons in the metal. When discussing strain gauges, we introduce the relationship delta is equal to by upon A, where R is resistance in ohms, rho is resistivity constant, which is a property of the specific conductor material being in the wire. It is measured in the unit of ohm. L is the length of the wire in cm and A is the cross-sectional area in cm2. In fact, rho is a temperature-sensitive parameter. With the knowledge of the relationship between rho and T for a particular metal, it is possible to construct on RTD with a specific relationship between R and T. C. Thermistors. A thermistor is made of a semiconductor material that exhibits a predictable and repeatable change in resistance as temperature is changed. Unlike a metal, the molecular structure of a semiconductor is such that increasing its temperature reduces its resistance. As the temperature of the material increases, electrons break free of their covalent bonds and conductivity is improved. The response function is as follows: RT is equal to rho e powers beta into 1/t minus 1/t01. 13. Where RT and rho are the resistances of the thermistor at temperatures T and at A, reference temperature, respectively. T and 2 are the thermistor temperature and the reference temperature respectively. In degrees Kelvin, beta is a property of A, material used to make the thermistor. The nonlinearity of the thermistor response function makes its use limited only over the most linear range of the device. Manufacturers of thermistors specify the useful range and the percent error over that range. 1.7 Smart sensors. The next stage of a sensor development is smart sensors, defined by the IEEE as a device with built-in intelligence, whether apparent to the user or not. These sensors are equipped with dedicated microcomputers for sensor-specific methods of signal processing. These sensors are also called intelligent sensors. The motivation behind the development of smart sensors are A. Compensation for the non-ideal behavior of the sensors, and B. Provision for communication of the processed data with the host system. Traditional sensors that are being used have varying requirements of compensation and signal processing objectives, and the number of measurements in industrial establishments is growing each day. The variety of variables, both physical and chemical, is also increasing, and newer sensing mechanisms are being exploited, increasing the load on signal processing, which already is much. Thus, for each variable, or rather each type of variables, a different processing is required, and with increasing number of types in industries, such load is becoming too much for a centralized computer. The smart sensor is intended to sense as well as do the sensing related processing within it. 1.8 Summary. Sensors can be broadly divided into two types: discrete and continuous. Discrete sensors are used in applications for which it is only necessary to know the state of the physical process being sensed. Continuous sensors are used when it is necessary to measure the magnitude of some physical property of the process. In this unit, we examined the components of a sensing system, which included a sensor